Thank you all for choosing to be here today. I know there's a lot of great talks at Apollo, and so it's exciting to have the room fill up right at the end here. My name is Jonathan. I'm an engineer on the GraphQL team at Block. If you're not familiar with Block, you might be familiar with some of the companies within Block, such as Square, where we have the card readers and the terminals that you might see in your favorite coffee shops or restaurants, or Cash App, which you might have used to pay somebody back for the coffee they bought you here at GraphQL Summit. Today, I'm excited to share with you a journey that some of our teams took this year to build what we called a GraphQL Copilot, using LLMs and Retrieval-Augmented Generation. Now, we built this during a hack week, and so I'm going to share what we were able to do during that week and share some of the successes and the setbacks that we encountered. There's a lot to cover over the next 30 minutes, so let's take a look at where this will go. First, I want to kick us off with a story, because that's my background. And I want to share some of the challenges that many of our users face in the GraphQL ecosystem. Next, I want to dive into some of the GraphQL and AI experiments that we ran that we used to tell a story to leadership about why we felt this was the right tool to solve the problems our users faced. Next, I'll guide us through the process of how we actually built the GraphQL Copilot during the hack week. And I'll wrap up with a couple of thoughts about the future of GraphQL and AI together, and more specifically, how we think we can evolve the GraphQL Copilot over time. So like I said, this starts with a story. And like any great GraphQL story, it's got to involve a migration. Inside of Block, we had an internal tools platform that was in the midst of a very large modernization effort. And part of our engineering strategy for this modernization was to have all of the teams, and there were literally dozens of them, contributing data to this platform, to move to GraphQL, to make that modernization effort much more easy and simple for the team to execute. And so as part of this modernization effort, the GraphQL team got to contribute docs, guides, and processes to help the teams who were brand new to the GraphQL ecosystem and paradigm onboard quickly and effectively. And once these teams were ready to pull the trigger and jump into GraphQL, we set up a couple meetings with them. The first meeting went about like you would expect. It's an introduction. People have read the docs. They have questions for you. We answer them. We'll show them a little bit about Apollo Studio and where to look for information, and then schedule a follow-up once they had some schema designed for us to interact with more directly. The second meeting was where we started to be a little bit surprised by our customers. And maybe we shouldn't have been here, but we expected the technical challenges to be the main ones that people had to overcome. But really, it was less about the service setup and infrastructure that challenged teams, and more adopting GraphQL and starting to learn how to think in the graph. At Block, we use a lot of RPC-based APIs, and what we saw initially was that teams struggled to shift from that design pattern into like where you might have an entity ID referring to another related entity, and shifting into the graph where you build the relationships right in. And we also saw that federation and understanding where data exists in the graph required some additional training for these teams. So during these sessions, we made a hard pivot, and we decided to show them very hands-on where everything was in Apollo Studio. We would use Explore to build up operations with them rapidly to address the challenges or the business problems they were trying to solve with the graph. If they had deeper questions on which other subgraphs were contributing to a type they cared about, we would show them how to use the schema search. And if they really had a need to see the deep context, we would use the very advanced tools like Command F or Command click inside of the schema definition language. But the biggest insight for us as we help these customers was that data discovery is really hard. And this becomes even more true as your supergraph grows over time. This is really true for Block. As of this week, we have 87 subgraphs, 365 fields on the root query and mutation, almost 4,000 types, and over 19,000 fields. Now I know there are a couple of companies here with supergraphs that are much larger, but even a supergraph of this size, it amounts to over 120,000 lines of schema definition. And that's way too much for a single individual or even a team of individuals to try and fit into their own head. So we wanted to find a better way for users to interact with this. And our first pit stop was visualization, right? Like, just make it less abstract, let's put it right in front of users. And this is a small slice of our supergraph zoomed out to 5%. And it's still an overwhelming bowl of gray spaghetti if you tried to interact with it. So after working with engineers and engineering managers and project managers and product owners, we had to ask, is there a better way? Now, around this time, I'm not sure if you've heard, but AI and large language models have kind of reached a fever pitch of excitement. And honestly, our team was pretty excited too. I'm a huge sci-fi buff, and this feels like we're living in the future. So we did the next step that made the most sense, and we asked ChatGPT, write a GraphQL operation using Square's public GraphQL API. And the results were honestly pretty good. If you look at this, you can see that the question we asked was, fetch the orders for the last month for our merchant. And the input, it has the fields for the date, and the fields in the response look like what you would expect if you wanted to learn more about orders. But when we brought this into Apollo Explorer, what we saw is a lot of angry red squiggly lines. It was close, but it wasn't quite right. And this is where we started to see a lot of hallucination from the LLMs. It invented the name of the filter. It didn't quite follow the right syntax. But we did learn something very important from this first experiment, as naive and optimistic as it was, is that the models can very effectively write what is valid GraphQL. So we started to explore, how can we make this better? Now, we were brand new to AI, and so we started building our vocabulary, and one of the first terms that really pops out immediately is prompt engineering. If you aren't familiar with the term, it sounds very official and like there's a whole new job for us out there, but all it is a pattern of getting better results from your models. One that really stood out to us as something that fit our needs was called zero-shot learning. This is also an overly complicated term that really just means giving the model additional instructions and context alongside the question or the prompt that you give it. And so we decided to say, okay, model, you can have our entire schema, and then please help us answer this question. And it immediately broke. It turns out that the models, like us, have a certain amount of information that they can fit in their brains at any one given time. They measure that capacity in something called a token, which you can think of as part of a word or a syllable, or maybe half of a word if you had to do some back-of-the-envelope calculations. We tried to pass it hundreds of thousands of tokens, rather than just the 16 to 32,000. But we're only building a proof of concept and trying to solve a very narrow problem at this point, so we decided to cheat. We set up a very simple prompt, and knowing the question that we wanted to answer, which is getting our orders for the last month, we actually went into our schema and plucked out only the types that we knew should be included in the response. And then, when we ran this against the model again, we got 0 angry red squiggly lines. It almost seemed too good to be true, and of course, in the long run, as we built out this project, we did have some other problems to solve. But this gave us enough confidence in the solution to try and look for opportunities where we could build out a less manual and more automated approach. And luckily for us, every year, Block runs a hack week where they encourage people from across the company to pitch their ideas and then join teams and build something for a week, whether or not you're on a team that is doing a pitch. And so for us, we pitched building this GraphQL Copilot and expanding these experiments, and we got people from across our internal GraphQL ecosystem who were pretty excited to contribute to it. So we dove in, and due to the experiments, we had a pretty clear set of ideas of what our requirements would be for that week. To start off, we knew that we would need to find a way to translate plain English or natural language into something that could talk to GraphQL. And we knew that we would also need to do some schema surgery. There's no way that 120,000 lines with the schema definition would fit into the context window, so we knew that we would have to find a way to trim it down into something that would. And then based on what we saw in our experiments with a little bit of prompt engineering, we knew that we would have to finesse the results and tune those a bit. As I mentioned, we are not GraphQL, we are GraphQL experts. We are not AI experts at this point in time. And so we had to do a little bit of research into what tools were available to us. And as you may have guessed from the title of this talk, the first one we came across was Retrieval-Augmented Generation, or RAG for short. And you did hear a little bit about this in yesterday's keynote, so I'll keep this portion of the introduction short. You can really boil it down into a simple two-step recipe. First, you retrieve some input from your favorite data sources. And second, you generate output with the model using that. And this technique was invented to solve two main limitations of the model. When a model is trained, it has a fixed data set, and that is, it stays the same even after the model is deployed to, say, OpenAI servers or Anthropic servers. And that training data is mostly public. So if you're building this tool for something in your internal APIs, it's not going to have any information about that. So we knew that we needed to find a way to feed the right information to the model, and the retrieval here really just means search of some sort. In the past, you might have tried something like a where and like clause in your SQL operations, or applying a full text search index to a database column, but that didn't really seem like it would fit the GraphQL schema very well. Luckily for us, so we had to answer the question, how do you search based on meaning? Luckily for us, data scientists have invented this concept called embeddings, which is a mechanism for turning a word or a document, or in our case, a GraphQL type, into a numerical representation. And those representations are very useful to us because we can perform operations like comparing the two of them and finding out how similar one is to the other. Now, as a software engineer, honestly, the mechanisms behind this are opaque, but we also have great APIs that we can work with them using. And when you compare one embedding, such as one that was generated from using a user's input, against a list of embeddings, say from a bunch of GraphQL types, you're doing something called similarity search, and the output can give you a list of a percentage for how similar each item in that list is to the user's input. Let's make this a little bit more concrete. If you've never worked with AI or built your own AI tooling, the first thing I would encourage you to do is go to your favorite LLM, such as Claude or ChatGPT, and just say, in your favorite language, generate a snippet to create an embedding. And you can see that the output is about 10 to 12 lines long, and it's extremely understandable. I love JavaScript and TypeScript, so that's what I chose here. And if we apply that to our GraphQL type, you can see that we do get back an embedding, which is that numerical representation. And it's gibberish to look at, but it's very useful to the large language models. And if we do the same thing with the LLMs and generate a snippet for getting, say, the top 10 or the top 25 operations, it will go through all of the embeddings, perform a comparison between the user input embedding and the list of embeddings, and find out which of those are the most similar. And it will give you the index of the items and the ranking as well. Now, this is a very, very simple example. You can dive very deep on using vector databases to do a very similar thing. But because we were doing this all in a hack week, we basically did this inside of a Jupyter notebook in Databricks. Okay, now that we have some grounding, let's take it back to the actual GraphQL Copilot project. We broke up the work that we wanted to do into 3 stages. The first was generating our embeddings. The second, in staging, we wanted to handle the user input, find the relevant GraphQL portions of the schema, and then in the third, we wanted to do execution, where we build the valid schema out of those types, send the prompt to the LLM, and then handle sending the response back to the user. Now, the two main areas that we found that were particularly interesting as we worked on this were generating the embeddings and then building the valid schema. And these were interesting because if you didn't do the first one right, you couldn't really generate a valid or useful schema. The first time that we tried to generate the embeddings, we took what we felt was the natural or obvious approach, which is generating one embedding per type in our GraphQL schema. We then generated an embedding for the user input. We grabbed the top 25 or 50 most similar types and fed that to the model. What we got was not what we expected. The initial result actually had as many or more hallucinations than the very naive example that we used without any context at all. And as we thought about it, it started to make a little bit of sense that the model actually was just seeing bits and pieces of an entire, like within the supergraph, and it had to invent the connections between those. And so we were actually encouraging the LLM to hallucinate a little bit more on our behalf to fit it all together. So we started to think more about how users, the original users that we were working with during this migration, actually worked with our schema the best. And that was, they would go right to the fields on the root query type. So we decided to do the same thing. Instead of generating embeddings for every single type in the supergraph, we decided to generate them only for the fields on the root query type. And then we did basically the same thing with the rest of the process. The only exception was, in addition to the most relevant field that we found, we also grabbed the return type for that field and included that in the response, or in the data that we provided to the model. And the results were a lot better overall. There were still some hallucinations though. And we noticed that the entry point, that field that we fed to the model, it was always correct, both that and its inputs. And maybe the first layer of the response was also correct. But if it got any more complex, that's when it would start to hallucinate. So we had to figure out how can we provide more information to the model. And we weren't sure how to do this at first. There wasn't really a good or clear way to merge the type and query first approaches here. And then somebody on the team that was smarter than me said, do we actually need an AI tool for this? And as we discussed it, we realized AI is not the solution to every challenge, even when you're building AI tooling. So here's what we decided to do instead. To build out what we eventually called a schema slice, we did basically a breadth-first search. So if you've been doing any LEET coding recently, this should feel very familiar. But when we got this field back, we knew the return type, in this case, a merchant. And so we would look at the merchant type, and we would pull off any custom non-scalar type and add that to our queue, and then walk down that list. So in this simplified example, we would get the merchant, the order, the amount, and the line item types, and build a valid schema just from those. And you can also see we have these additional types here, like hardware device or accessories or location, which wouldn't be relevant to that original query that we tried to build. As we did this, we did run into some sharp edges. For example, a breadth-first search on a very large type like this merchant was, it would immediately try and grab far too much of the overall supergraph schema, and it would bloat or overflow the context window almost immediately. So we had to put in some rules to handle that. We also needed to handle inconsistencies in the schema design. We had some legacy supergraphs that really had more of that RPC style in them, and so we needed to give the LLM rules for how to handle that, such as, don't be afraid to chop this up into multiple operations to solve the business problem. And last, we were trying to help people coming to the graph for the first time. So their data may not be in the graph quite yet, and so we needed to be able to efficiently detect if this is a low confidence match, then go ahead and exit early and tell them that there's not anything here. And as we started to build all of this into the Copilot, the hallucinations were mostly gone. I think we had around 80 to 90% of the random queries that we ran were yielding very, very good results. And most of the next steps as we ended the hack week were really about fine-tuning the output of the prompt, which brings us back to prompt engineering. One of the things we saw was that when we gave the LLM as much schema as we could fit into the context window, if we kept the slice as large as we could, the LLM decided to return the favor and threw us a kitchen sink of all the fields that it could. And so we told it to try and be a little bit more efficient in solving the problem and have fewer fields in the response that it returned to us. And sometimes the responses were non-idiomatic. So it was like asking somebody who hadn't used a lot of GraphQL before, try to write a GraphQL query. But if we just said, adopt the persona of a GraphQL expert, we saw that it refined its results just enough to make it a little bit better. And this last one, if you've ever rushed on a Friday and tried to use a model and gotten unexpected results, you are not alone. We started to see, instead of actually giving us back operations, it would just leave comments of like, fill this in here or to do. And so we followed some recommendations that we found online of actually offering a cash reward or a tip to the model, and that seemed to improve the results at times. Like it would for us, right? So what does this look like in practice? We were able to, once we had finished the hack week, we took a couple of different examples and we started to put them in just to see, is this producing something valid? So for Square, where it has terminals and card readers, we would ask, what hardware devices would a given merchant have? And you can see that the model did a pretty good job of adopting idiomatic GraphQL that fit the actual pagination patterns within our supergraph, and then pulled out a few relevant fields. And if we do something completely different for a different business unit, for something like cash, where let's say we're helping a developer build a component in React using a cash customer profile, it pulled out a completely set of different information. The schema slice fit into the context for the model and returned something just as useful as that first example. And if we ask something slightly absurd, it does a very good job of exiting early. So this was a hack week project, but we did want to check our work along the way. And so as you're trying to build these proof of concepts and bring GraphQL and AI to your own companies, what we would recommend is don't over-invest in this early tooling. You can get a very long way by just doing something like copying and pasting the results from the model into Apollo Explorer, or doing a quick API call to see did it fail with missing fields in some way. You can also compare against known use cases. The supergraph has been at Block for a couple of years now, and so we knew where a lot of our most frequent operations were and what problems they tried to solve. So we rewrote prompts, fed those to this new GraphQL Copilot, and compared the results against those known operations. And at Block, we also have different versions or variants of our supergraph. Some of them serve our internal users, as is the case with this modernization effort, and some of them are for third-party public developers. And so we fed different versions of our schema into this tool and different sets of embeddings, and then compared the output between the two. So where do we think that this GraphQL Copilot tool can go in the future? Overall, we think that there's still room to improve this schema slicing approach. It worked very well to improve the overall results and reduce hallucinations in the output. But if we had to do it again, we might consider applying the similarity search at the field level as we iterated through that breadth-first search. We're also excited for the possibility this represents using data integrations. So not only generating these new operations dynamically, but being able to feed those back into an application using live data and say a live cash customer ID or Square merchant ID. Now, we got very far into the removal of hallucinations from the results, but it's still not perfect. There are some periods where the model will say, oh, you want to have a profile, and maybe 1 in 5 of those cash customer responses would include an email field that doesn't exist. And so we would want to be able to provide additional tooling to automatically prune those before running them for the user. But we do see amazing potential with this type of tool. It could be built into a Chrome extension. It could be attached to a VS Code extension or plugin, maybe even integrated with the new Apollo language server that they've been demoing a lot this weekend, though I haven't had an opportunity to play with that yet. So as we wrap up, there are two key takeaways that I hope that you all receive from this talk. First, large language models and retrieval-augmented generation can work very well to address challenges in the GraphQL ecosystem, particularly as the schema grows larger and larger. We really do believe that having a natural language interface for our GraphQL schema will be much easier for teams to use to explore than some of the existing search and visualization tools. And next, AI is more powerful when you use it with existing engineering practices. AI isn't going to replace us. We are going to build more powerful applications and tools using those together. Thank you so much for your time and attention today. If you have any questions, I'd love to chat.